Welcome back, everyone. We're going to be solving LeetCode 872, leaf similar trees. So we are going to consider all of the leaves of a binary tree from left to right order. The values of those leaves form a leaf value sequence. And they say, for example, in the given tree above, the leaf value sequence is 6, 7, 4, 9, and 8. Two binary trees are considered leaf similar if their leaf value sequence is the same. So we need to return true if and only if the two given trees with the head nodes of root 1 and root 2 are leaf similar. Okay, so we need to first understand what a leaf node is within a tree. And a leaf node is going to be a node that does not have either a left child and a right child, right? It cannot have any children at all. It has to be the very last node. So, knowing that, right, we can use depth first search in order to solve this. We can use a depth first search on our tree 1 and on tree 2 and traverse all the nodes until we get to a leaf node. When we find a leaf node, we can append it to a resulting list, which is going to be referencing the leaf nodes in our tree 1, and then we'll do the same for tree 2, and then we can just compare the two output lists at the end, and that will give us our answer. So, depth first search, right, we have to remember it uses a stack. So we know we're going to have two stacks. Well, you will call them stack 1 is going to contain the root 1 tree, and we will have a stack for our root 2 tree. And like I just said, we're going to have two resulting output lists, which we will compare at the end. So we will say res, well, let's call it leafs 1 and leafs 2. Okay, now we need to run depth first search twice. So we'll say while the length of stack 1 is not equal to 0, that means we can do some stuff, right? We can run our algorithm. And we will do the same thing for stack 2, for our second tree. And then at the end, we are just going to return the value of leafs 1 equal to leafs 2. So if all the leaves are the same, right, these two resulting arrays should both have 6, 7, 4, 9, and 8 in them, respectively. So, depth first search. What do we have to do first? We have to get the node off of the very back end of our stack. So we can say node is going to be equal to stack1.pop. And we can do the exact same thing for the second tree. Node is going to be equal to stack2.pop. Okay, after we have our node, what do we have to do? We have to check if that node is not null. So if node is not none, we are going to do some things. And we can do the exact same thing for our second tree, right? Okay. Now that we know our node is non-null, or if it's non-null, we can simply say, all right, well, now I want to check if the left and right nodes exist. So we'll say if node.left does not exist, so we'll say is none, and node.right is none. So what does this mean? This means that the node does not have a left or a right child, which means this is a leaf node. So when this condition evaluates to true, we want to say leafs 1 dot append the current node's value. And we will do the exact same thing for our second tree, except we will append the value to leafs 2. Okay, now we can go about our regular checks of adding our nodes to our stacks. So now we can say if node.left exists, so is not none, then we can say stack1.append node.left, and I'm going to do this in a pre-order traversal, so I will say the right side first. So if node.right is not none, we will say stack1.append node.right, and then we will go left. Okay, perfect. Now we can do the same thing for our second tree. If node.right is not none, we will say stack2.append node.right, and then go left. Is not none, stack2.append node.left. Okay, now that should be it. Let's get rid of some spaces here and we will run this. I don't think I made any other mistakes. Stack2 is not defined. Okay, right here. Okay, so it passes both test cases. Let's submit this. And it does run. It's perfect. Okay, time and space complexity. Time complexity is going to be O of n plus m, where n is the number of nodes in our first tree and m is the number of nodes in our second tree, right? We have to traverse all of the nodes in the tree at least once for both trees. So that's going to leave us with a time complexity of O of n plus m. The space complexity is going to be bound to the length of our stacks that we're using for our trees, for our depth first search traversal. So that is going to be bound to O of stack1 dot length plus stack2 dot length. And we could also say it's also bound to the leaf outputs as well. So we can also say plus leafs1 dot length plus leafs2 dot length. All right, that'll do it for LeetCode. What number is this? 872.